We have seen in detail lexical analysis phase and syntax analysis phase. So now we can have a discussion on semantic analysis. Semantic analysis, as you know, it comes after syntax analysis phase and precedes code generation phase. Now, what is the importance of syntax analysis? It adds not syntax semantic analysis, it adds semantic information to the parse tree that we have created in syntax analysis phase. And it also performs certain checks based on this information. Okay, the semantic analysis phase adds semantic information to the parse tree and it performs certain checks based on this information. Now, examples of this semantic information that is added and checked is type checking and object binding. So, you know what is type checking, right? So, if you have declared a variable as integer and you are storing that variable as a real number, then you will get an error. Similarly, object binding means the function name and attributes. The proper binding of this function and its attributes comes in object binding. So these are all performed in semantic analysis phase. And in this semantic analysis, some early code optimization will also be performed. So, what are the things that are performed during semantic analysis? 1. Disambiguate overloaded operators. So that means if you perform some operator overloading, for example, you are using plus sign for concatenating two strings, you should specify that. Okay, so that data will be properly recorded in this semantic analysis phase because after this phase we are moving on to code generation. Second is type checking. As we have discussed, type checking will be performed. Then uniqueness checking. Uniqueness is nothing. It will check whether a particular variable name is used in more than one instance. For example, I have declared int a, and after some time, I'm declaring character a. So same variable name came in two different declarations. So that is called uniqueness checking. Now, type cohesion. What is type cohesion? In some languages, it will upgrade the data type. For example, if you have used integer data and real data in addition process, it will be automatically converted to real data. The result will be converted to real number. So that is type cohesion. Certain programming language will support that, certain will not support. So they that all checks are performed in semantic analysis phase. Then name checks, it's similar to that. We have seen the same name has been uniquely used or whether it is used repeatedly. That is what it is checked in name checks. Now the semantic errors that can occur while you're going through this phases: type mismatch. Okay, so then undeclared variable, a variable that has been used but is not declared yet. Then multiple declaration of variable in a scope, more than one declaration within a scope. Then accessing an out of scope variable. Okay, then actual and formal parameter mismatch. So these all are the errors that we can um, and we come across during the semantic analysis. Now, syntax directed translation. So it is done. So we have already discussed that after generating parse tree, we are going to the syntax, semantic analysis phase. So, and we will have some additional information to this parse tree for performing semantic analysis. So, that is explained here. Syntax directed translation is done by attaching rules or program fragments to predictions in a grammar. So in syntax analysis phase, we were using a context-free grammar and we generated parse tree based on that. Now we are attaching rules or program fragments to productions in a grammar. So some basic things that we want to understand. One is an attribute. Okay, what is an attribute? Any quantity associated with a programming construct is called an attribute. It can be an integer, it can be a string, it can be a line of code, anything. Now syntax directed translation scheme means it is a notation for attaching program fragments to productions of grammar. So we get syntax directed translation by attaching some program fragments to productions. So how it is attached? It is explained by syntax directed translation schemes. Now the principle of syntax directed translation states that the meaning of an input sentence is related to its syntactic structure, that is to its parse tree. Okay, with the parse tree, using this parse tree we are generating what performing this semantic analysis. So this syntax directed translation, it states that meaning of an input sentence is related to its parse tree, and we associate attributes to the grammar symbol representing the language constructs. Okay, to the productions we will be attaching some attributes, and values of these attributes are computed by semantic rules associated with grammar productions. So we will be attaching some attributes to the productions, and value of that attributes will be, we will get that value by performing some semantic rules. And why, after this getting the evaluated result, we will use it for generating a code or insert information in the symbol table, perform a semantic check, or issue error messages. So this is the basic concept in this semantic analysis. First, for each of the productions we will attach an attribute, then we will evaluate that attributes based on some semantic rules. There are two ways to represent the semantic rules. First is syntax directed definition or SDD, and syntax directed translation schemes or SDT. So these are the two methods by which we can represent the semantic rule. So first we will see syntax directed definitions. That is what we have discussed already. That is, grammar symbols have an associated set of values will be there. Predictions are associated with semantic rules for computing the value of these attributes. And such formalism generates annotated parse tree. So we had input parse tree. After going through these steps, we will get annotated parse tree. Okay. What is the difference between parse tree and annotated parse tree? An annotated parse tree will have a node which is a record with a field for each attribute. For each attribute, we have an additional field. For example, capital X is an is the grammar symbol and A is our attribute. Okay, so this is a record. Now, the value of an attribute of a grammar at a given parse tree node is defined by a semantic rule that we have discussed. Now, what is an attribute grammar? Okay, so I have already mentioned that attributes are properties associated with grammar symbols and can be numbers, strings, memory locations, data types, etc. Now, an attribute grammar is a special form of context-free grammar where some additional information are appended to one or more of its non-terminals in order to provide context-sensitive information. Okay, whenever we add some attributes to the predictions, then it is known as attribute grammar. Now the medium, it is a medium to provide semantics to context free grammar, and it can help specify syntax and semantics of a programming language. So if you are asked to write a definition for attribute grammar, you have to write these 3 points. Okay, these 3 points come under the definition. Now, when viewed as a parse tree, it can pass values or information among the nodes of a tree. For example, this is a prediction that we have seen earlier, right? E giving E plus T is a prediction in a grammar. Now, I have added a particular rule to that. This rule is specified within curly brackets. E dot value equal to E dot value plus T dot value. So this is the attribute that I have added, and the rule is stated within this curly bracket. Okay, so the right part of CFG contains the semantic rule that specify how the grammar should be interpreted. So what does it mean? I should get the t value, that is the value assigned with the non-terminal t. Then I should get the value associated with non-terminal e. Then I should add both of them, and it is assigned to this e value. So this is the rule. So okay, semantic attributes may be associated to their values from their domain at the time of passing and evaluated at the time of assignment or conditions. So how the attribute is assigned value? At the time of passing, it will get the value. Okay. Based on the way the attribute get their values, they can be broadly divided into two categories: synthesized attributes and inherited attributes. So we told that we'll be having predictions, we will associate rules, and for these attributes we will evaluate the attributes. So how the attributes are getting evaluated, either we can categorize into synthesized attributes and inherited attributes. Now we'll see how they get their values. First is synthesized attributes. A synthesized attribute at a node, it is computed from values of attributes at children nodes. Okay, we have a parse tree, and you know that there will be a parent node, there will be children node. So a value of attribute at a particular node is taken from the value of children node. Then it is known as synthesized attribute. For example, as giving ABC is a prediction. Now attribute attaching attributes s dot a equal to a or dot a comma b dot a comma c dot a. This means that the value of the attribute of s can be any one of a or b or c. Okay, so then it is known as synthesized attribute. Now, how computation of synthesized attributes are done is with an example. So first we have to write the SDD using appropriate semantic rule. Then you have to compute the annotated parse tree. Okay, then the value obtained at root node will be the final output. Now we'll see the example in detail, then you will get a better clear understanding of this. So this is the production or the grammar given as giving E giving E1 plus T, E giving T, T giving T1 into F, T giving F, F dot digit, F giving digit. Here you have to mention one thing. In this production you can see E giving E1 plus T. This E1 is same as the non-terminal E. These two are same. But why I have given this one is to understand that value of E1 and T are added and is assigned to this. Okay. So if I write E here, the parser will get some confusion where to store the resultant value, to this E or to this E. So for avoiding that, we are naming the attribute this on the RHS as E1. Here also you can see. So if the LHS has a non-terminal same as that will come in RHS, then you have to give this 1, 2, etc. in order to understand that this is the head. Okay. These are the semantic rules. Okay, so as giving E, I am giving the semantic rule as print E dot val, that is how to get the value of E. Okay, this is the attribute value. So first we have to get the attribute value, then print. That is a semantic rule associated with this. E giving E1 plus T. First I have to get E1 val, then T val, then you have to add and have to assign to E val. This is a rule. Similarly, we can see all this. So the last one, I have giving digit. So digit means it is a terminal symbol. So all terminal symbols will be assigned some values either when we are during in the compile time or in the runtime. It will be directly given. So that is why it is mentioned as lexval. That lexical value has to be assigned to the digit. Okay, and it is assigned to f dot value. So whatever value you are giving to digit will be assigned to f. Okay, so this is a rule. Now how we can generate the past. So let us assume that this is our input. Okay, 4 into 5 plus 6. For computing, synthesize the attributes. Now, what is an annotated pass tree or decorated pass tree? Containing value of attribute at each node for given input string. It is called annotated parse tree or decorated parse tree. You should have the value of attributes at each node. Now, this is our grammar, right? And I have to get parse tree for this. So how I can get this? Our starting symbol is s. From s I have to get e. Okay, from e I should take e1 plus t, and for e1 plus t or t1 star f, then right. So then only I will get 4 into 5 plus 6, right? So this is from this I will get this one. So how I am assigning the values is, you have to assign values from top down and from left to right. Okay, how to do top down and left to right. Now here I don't have value now, e dot val I don't have now, here also I don't have, here also I don't have, here also I don't have. When I reach here f dot val, I have the digit 4 as the input. So what I will write, digit dot lexval equal to 4. So I assign this digit dot lexval equal to 4. Now I have f dot value equal to digit dot lexval. So I assign this 4 to f dot val. Now t dot val equal to f dot val. So I have assigned t dot val as 4. Now I got t dot val here. Here I have multiplication operation. Then here again f dot val. I will get f dot val only from digit dot val, lex val. So I got f dot val as 5. Here I will perform 4 into 5, 20. Okay. Then this 20 is assigned to e dot val by this rule. Okay. E dot val giving t dot val. So from this rule I got 20 here. Now plus here right I will get f dot val from digit dot lex val. From f dot val t dot val I get, and from these two values I get e dot val as 26. So this is called annotated parse tree generation. Okay, you should get the value of each node for the input string. Now, what is inherited attribute? So, inherited attribute is one in which the value is that for particular node will be we'll get that particular value either from its parent or from the sibling nodes. So, in the case of A giving BCD, this C will get value either from A or through B or D. So that is represented here. C dot in equal to A dot in, or C dot type equal to B dot type. Okay, C type can be assigned either from B or T, or can be inherited from A. Now the steps for getting initially are same. First construct the SDD, then get the annotated parse tree, then calculate the attribute values in top down manner. So this is a set of grammar, and this grammar, it is it specifies a declaration. Okay, so D giving TL. So T is the data type and L is the attribute. Okay, so if I am giving int A, it is the grammar that is described here. Here it is the data type. So data type can be either integer, float, or double, and L is the variable. So variable can be either one variable, that is why it is given L giving ID, or it can be more than one variables. For example, int A comma B comma C, then I should give this protection so that L can be repeatedly given. Okay, so how we are writing the rule? So D giving TL, this inh means inherited attribute. Okay, so this T is the data type and L is the variable. So the variable's type is inherited from T dot type. Okay, that is why it is given like this. Then T dot type is integer given directly. Here T dot type is float. Here T dot type is double, and here id we have to get from inherited variable. This id dot entry means we will enter id, right? So it is already there in symbol table, or we will get either from runtime or from compile time. That is why it is specified as id dot entry comma l inherited. Then enter type means we have to enter this value in symbol table. That is why the rule is specified like this: enter type id dot entry comma lnh, and that inherited value is assigned to L1. So these are all examples for inherited attributes. Now this is an annotated parse tree. So here the value is obtained from parent. Here I am giving A. Now this which data type it has to use, it is this from this parent get. Similarly, this will get from the sibling. So this is an example for inherited attribute. Now implementing syntax directed definitions, we have two methods. Okay, first one is dependency graph and second one is evaluation order. Now dependency graph is the simplest and most general technique used, and it uses this annotated parse tree. Now we know that annotated parse tree contains nodes, and what this dependency graph uses, it will see there is a node for each attribute. Okay, we will create a node for each attribute, and if attribute B depends on an attribute C, there is a link from the node C to node B. Okay, if attribute B depends on an attribute C, okay, only after evaluating C I will get the value for B. That is what it means. After evaluating C only, I will get the value for B. So then there will be a link from node C to node B. It can be taken as the value of C is passed to value of B. So in this type we will represent the attributes. Okay, attributes will be represented as nodes, and there will be arrow marks from each node denoting which one has to be evaluated first. So dependency rule is if an attribute B depends from an attribute C, then we need to find the semantic rule for C first, then the semantic rule for B. So this is how we will represent it in dependency graph. Now, so this is an example. Now E dot val equal to E1 dot val plus T dot val. So first I have to evaluate E1 val, then T val. The result is stored in E dot val. So this information is passed there. That is why the arrow is given like this. So we have seen the predictions for dependency graph. This is the annotated parse tree. So how the graph is shown is here. First we will take the value of 1, so it is given like this, right? And this L will get from inherited, so that is why it is given like this. From parent it will get to child. That is why the arrow is like this. Similarly, from here it is passed here, from sibling to sibling. So that is why the arrow is like this. So this is how dependency graph gives a clear idea. Evaluation order is another method. So if there are more than one nodes, what we will write is we will write the nodes one by one. For example, from 2 it is passing to 3, from 3 it is passing to 4, from 4 it is passing to 5. Then we can write 3, 4 and 5 in linear order. That is called evaluation order. Now the problem occurs when this graph contains a cycle. Then we cannot perform what ordering often of that elements or nodes. So in that case we will say that we cannot evaluate SDD on this parse tree. So this is for today. So we have seen what is the importance of semantic analysis, what is SDD, so how we can write SDDs. So we will continue in next tutorial.